It's tight. No, no corrections are fine. It's appropriately named.
20 per
Final. So last time, let's see if we remember how to do this. So Z is kind of like, and this was a question from earlier, so we'll hopefully we'll pick that up on the way. Z is kind of like our general complex number variable. So Z would be some kind of A plus BI. So last time we talked about how we can graph these things. And this graph, I always found this graph to be sort of lame, to be honest. It's almost too easy of an approach of how to look at complex numbers, but it leads to a beautiful way to rewrite this. So in that case, it's not so lame. I have the real part, the imaginary part. So one level of this homework is going to be crazy easy. If I wanted to graph that,
What is 8.3 again? Is that what I heard?
yeah, this is 8.3. I want to graph this. How far do I go on the x-axis?
3 back.
The real axis. 3 back, and then 4 up. No worries. So if you have a graphing problem, good God. Accept that it's easy. Do not make it more than it is. That's all it is. So that part's easy enough, and it seems too easy to really think that it really leads to anything useful, but it really does. I can now rewrite this complex number in a different form. So I can rewrite any complex number in the form, oops. And why does it make sense that the sign is there? Because the imaginary is the y-axis, and there you go. So the sign should be with the I, because that's the imaginary axis, is the y-axis, and the sign lies y. Cool. So it kind of makes sense how this thing is put together. R would be what? So for here, R would be this distance. How would you get this distance here? Yeah. -3 squared plus 4 squared. Square root. We end up with 5, right? We're at 3, 4, 5 triangle. So in general, how do you get it? It's just going to be the square root of a squared plus b squared. And the really kind of new thing here is this use of angles to represent. It's not really new. It's certainly not new. Because remember a while back we talked about how to convert between polar and rectangular. X was r cosine theta, y was r sine theta. So you can see the x, r cosine theta, and the y-axis imaginary, r sine theta. Cool. Maybe.
You're adding?
Okay, maybe. And theta here is going to be the inverse tangent, or actually, let me write it more generally. Tangent theta is b over a. Which still matches with the idea of tangent. What's tangent fundamentally defined to be? Y over x. Imaginary is the y-axis, and the y, so it should be the b over a, y over x. Same exact idea. Yeah. Second. So to look at the same thing here, here's theta. Right, actually theta is this, but this is kind of like the referencing. So here's theta. This would be our cosine theta. This would be our sine theta. Everybody with me on that? So if this is our sine theta, and this is our cosine theta, then I can rewrite -3 plus 4i as r cosine theta plus r sine theta I. Because those coefficients are these expressions. Yeah. R is the same thing as it's like that radius. So it's really taking the place of d, the distance. Yeah. So it's the distance from the origin to the point, as the crow flies. Yeah.
Why are we looking for tangent and not like sine?
I need to define what theta is. And here's the definition of what theta is. Tangent of that angle would be b over a. That gives me a way to figure out what theta is.
Oh, it's the same.
Yes. Cool. Okay.
So in order multiply data, like to finish solving that problem, we have to go like inverse tangent or something like that? Or...
Yes, I love it. And you just got to be careful that you end up in the right quadrant. Okay.
So there's no eyes in the tangent line?
There's an I here, and tangent's really just going to be related to the coefficient of I. So coming back, looking at this another way. So here's the 3, here's the 4. So that's 3, that's 4. Negative 3. Here's the theta. Now I can write this as negative 3 plus 4i. We know that. But again, tell me, and this is 5, so what is this really in terms of theta? What is this side really in terms of theta?
Cosine.
So it would be, yeah, 5 cosine theta. You guys with me on that? That's certainly 5 cosine theta. So again, let's take a step back. What's cosine theta for that triangle? What's cosine theta? Negative 3 over 5. Therefore, negative 3 is 5 cosine theta. You with me? So couldn't I replace here? What is negative 3? What did we just say it was? 5 cosine theta. What about 4? Yeah, this would be sine theta equals 4 over 5. So 4 equals 5 sine theta. So what can I write here instead?
5 sine theta.
5 sine theta. I. So let me put the I there. Right, so I can take a 5 out. Okay. So how does it relate to what I said here? What was R? 5. So I have 5 cosine theta plus I sine theta, like we just said there. Yes, ma'am.
I have a question. I know probably you already went over it, but so we treat like cosine and sine when we're like solving for it. We just treat it like a regular like x or y in any other given case. Because I noticed that you divide and you multiply it, but you leave cosine data or sine data by itself. Like you can use like the substitution method in a way. Because that's what threw me
Are you
off.
talking about like when I do cosine theta equals negative 3 over 5? And then solve for negative 3?
Or like,
Is that?
or let's suppose you had cosine data 5, the other way around. All you do is just divide by 5 and then, okay. That threw me off completely on the test. I didn't know to treat it like a regular variable.
So, yeah. So cosine theta is a function. Cosine is a function. Just like the square root is a function, the natural log is a function. You with me? So just like if I had natural log of 7 equals x over 2, how would you solve for x? Multiply the 2 up. Do I do anything special with them? No. Can I make it natural log of 14?
No.
Hell no, right? That 2 just can't come inside that function.
But
So here I couldn't make that suddenly go in there or something interesting, right?
no. But like in the quiz you had something with like a 3 data, and you just said at the end we should have divided. I didn't know we were allowed to separate that 3 from the data. That's where it got me confused.
I'll show you how to take that. So it's a little trip down memory lane. How do I solve that for x? What's the first step? Didn't mean for it to be difficult. What's the base?
E.
How can I rewrite this then? Right? And then how do I keep going? What's the last step? Divide by 3. Because what does it mean when 2 things are sitting next to each other? Multiplication, right? So if I'm trying to solve for x, I divide by. If I'm trying to solve for theta, if I get 3 theta equals pi over 2 plus 2 pi k, for example.
You divide.
Yeah, divide.
Yeah, divide everything by 3. Because what I really need is theta. Then theta is pi over 6 plus 2/3 I k. Or however you want to write that. Nothing amazing. So anytime I'm trying to solve for x, what do I, and this is what I was telling You know, back in algebra, I don't know if your teacher ever said this, but you almost always do what last when solving an equation? Divide. You almost always divide last to get rid of whatever coefficient's in front of my variable. So there's nothing new there. Yeah. Okay. Well, let's do one more example like we just did. Let me really hammer this home. So if I have the complex number -2 minus 3i. So I go on real axis, my imaginary axis. -2 minus 3i, so I'll go ahead and do that. That shouldn't be a big deal. So here's that angle that we're talking about here. Okay, so this is -2, this is -3. What's this r going to be? Square root of 13, yeah, 4 plus 9, so square root of 13. Okay, cool. Is that so far so good? Is that right? I know we're talking about imaginary and real axes, but they're basically xy axis, nothing major there. So I can plot real versus imaginary. Then I can find this distance if I wanted to. But what that allows me to do now is, what would cosine of theta be? Yeah, the x piece over the hypotenuse. So -2 over root 13. We'll go ahead and do that. Yes, ma'am. Well, we won't do that.
Okay, hold on.
Not get too far away from where I was.
Can you just pretend the eye isn't there?
The eye isn't there. Is it? Is the eye there? So why is there an eye here? And that just tells me which axis that goes on, right? That's the eye axis. This is the real axis. So every step here is a step of 1. Because I could say this is -2 ones. Every step here is a step of eyes. So it's built in. It's the scale. The eye is part of the scale of that axis. So it's a good question. That's where it doesn't disappear. It just tells me how far to go on that axis. Because it's scaled by
It's just letting you know
eyes.
that you're on the y-axis.
Exactly.
And why did they change to eyes instead of Y's? Why did they have to make it more complicated?
No. So we all understand that complex numbers exist. What's one place complex numbers comes from for us? Now that's what part of a complex number. Where do they come from? Where could they come from? Yeah, when I have quadratic formula that I have to use or something, or when I have an equation like x squared plus 25 equals 0, that only has complex answers. So complex numbers exist. So we have to deal with them then. So one way I could try to make it easier to deal with them is figure out, is there a better way to write them? And I do not blame you at all if you don't yet believe that it's better to write them in the way that I'm trying to write them. Because it does not look easier. But what we're going to do today, hopefully, is show you how a lot of the math that I have to do is easier when I write that in a different form. Yeah.
Theta, it's going all the way from that side all the way around, or would it just be the surface?
So there's a reference angle here, certainly.
Oh, okay.
But here's the actual angle itself.
Okay.
Okay. Yeah.
So the answer -2 root 3 equals 3 cosine theta?
No.
I'm not sure what happened. So here, I'm trying to describe this side in a different way. So I want to solve this for -2. So I would just multiply that root 13 up, right? So this side, which is -2, I can also call it root 13 cosine theta. So far, so good? And this side, which is -3, it's going to be sine theta. So I can also call that root 13 sine theta.
What other side?
Okay. Yeah.
Put the root up. Do you get rid of the root?
I did, because I automatically do it, but I knew I was going to multiply it up anyway. So is there any radicals in the bottom? No. There was for a second, but I'm going to multiply it up anyway. So I did rationalize it, and then I'm like, no, I don't need to do that because it's going to come up anyway.
Okay.
But if you, had you rationalized it, it would have just been a 13.
Don't. In fact, really, everything I'm doing right now, you will never, hopefully, ever do because it's unnecessary. What we're doing right now, don't even give me that look. What we're doing right now is I am desperately trying to make sure that you understand why this other format works. That's all I'm doing right now.
Okay, now.
Because it's apparent that it doesn't make sense. So I'm trying to show you how you can actually do this work, which you don't need to do, because there's a much quicker way to do it. But you could do this to really see where all the parts are coming from.
Would you rather?
So everything we've done so far, all this stuff we've done so far, is stuff we could have done back in chapter 7, right? In fact, we did this stuff back in chapter 7. Ignore the I. This is the axis. All right, so let's put this together. So another way to write this complex number, another way to write it, what's -2 also known as for this setup?
Root 13 sine.
Root 13 cosine.
Cosine theta.
And what's -3i also known as?
Root 13 sine theta, so that will equal root 13
Thank you.
parentheses. Blah, blah, blah.
So I just replaced -2 with what it is. I replaced -3 with what it is. Brought out the root 13. Now what's theta? What's the definition of theta in this case? Yeah, -3/2. It's got to be y over x, right? So what's theta going to be in this case? Can somebody help me out? Got their calculator out?
I don't know where I left it. I left it.
56.
0.31.
So what's the real angle then?
56.
That's a reference angle. What's this whole length? Plus 180. Cool. So 236.31.
How do you know it's plus 180? Oh.
Because I know where it is. Okay, so the last thing I want to do here, I already just got this here, right?
Yeah.
So what we just did, and I'll show you the shortcut. This is the explaining part. Explaining part is not necessarily what you're going to do yourselves. This is just explaining why it works. We'll do another problem in a minute to show you the nuts and bolts, how quickly it is if you don't do all these explaining steps. All right? So what we just showed is that this can be written as root 13 cosine 236.31 plus I sine 236.31. All right, isn't that what we just showed? We replaced that with what it is, that with what it is, and factored out the root 13. Now, a whole other way to write this, real quick. If I wanted to use the reference angle instead, what do I have to be careful about? I've already written something incorrectly.
Minus.
Good, it's going to be negative. So there's two different ways you can write that. Sort of related to in polar, you either turn and walk forward, or you turn and walk backward. It's the same idea, right? So here I'm turning and walking forward, or here I'm turning and walking back.
So what are we solving for? I'm sorry, for C.
All we're doing is rewriting this in this form. So, it
I
is.
thought wouldn't it be easy just to jump to tangent theta or?
How do you mean? Sorry. This tangent theta step helps me figure out what that theta is. That's all it
what I'm
does.
saying. That would be like easier instead of going through all the.
Yes. Now again, I hope to God nobody does it like this.
Okay, I want to see the shorter.
Oh, help me God. So,
He always likes to go
at
through
this
the
point, you
shorter.
should know me as a teacher. I desperately try to show you why things make sense. And it made sense. To me, I could see that a lot of people are having trouble why things kind of work the way they did. So let's do a problem exactly the way that you should do it in homework. You don't have to show yourself this every time. That would drive me insane. But now that we've seen the real nuts and bolts of what's behind it, how quickly can we do a problem directly? So if I have a complex number like this here, let's do
3i.
3i.
It shows up 2 plus
That would be on the
AI
fourth quadrant.
as the answer.
which one? Sorry.
That root 3, or negative root 13 cosine plus I sine.
I don't know. These would both be positive, wouldn't it? It's in the first quadrant, so the whole thing should come out negative. I'm not sure what to tell you. What quadrant am I in for this?
4.
Yeah, because I'm in 2, -5. Okay. So to put it into this format, I can just do directly. What's R going to be? What's my A? What's my B? Let's start there.
20.
What's A?
2.
2, and what's B?
-5.
-5. So B is always a complex, and you can remember that because it was the second thing you learned is complex. You start with real numbers, that's part A, and then part B of learning is complex. So remember, B is the complex piece, A plus BI. So R would be,
Square root of 29.
yeah, square root of 2 squared plus -5 squared, so root 29. And then theta, tangent theta has to be,
2 over -5.
careful,
No,
5 over
-5
2.
over 2.
B over A, Y over X, yeah. -5 over 2. So somebody help me out, what would that be there? What do you get from your calculator for that?
-68.
Oh, it's a negative in there, by the way.
-68.1985.
So we'll say -68.2. And actually that directly matches, doesn't it? Isn't that -68.2 there?
Yes.
Which is also known as what? What else could I say that was?
Like 180 minus that.
No. 360, yeah.
That's what I
So it'll be like, what would it be? 291.8?
291.
Cool. All right, so you can write either way. It's sort of convention to use the positive one, but it doesn't really matter. So how do I rewrite this then? I can just fill in the blanks here. R equals, oh, sorry. Z equals R, which was root 29, cosine theta plus I sine theta.
It kind of makes sense.
And that's the way class works. You don't understand it for the first few minutes. You work, and then it starts to make sense. So allow that to happen. Don't immediately mutiny.
we have to keep I.
When we rewrite it, we keep I, right?
Yeah, I.
I.
It still has to be a complex number. If you did root 29 times cosine of 291.8, in fact, do that. Do it. Do root 29 times cosine of 291.8. Just humor me. See what it equals.
2.
Yeah.
Where'd you get to 91.8? Where'd you
So you guys are cool with me here?
Yeah.
Right? And that's a negative angle, which is not terrible, but it's just convention to use positive in there. So the actual angle we're at is 291.8. That's 360 minus this, or plus this really. Right? If I go back 20, that's the same as going forward 340.
I is in the square, negative square root,
I is the root -1, which is basically 2. And why did it come out exactly 2? Because we rounded here, right? Okay. And of course, amazingly enough, if you do root 29 times sine 291.8, you're going to get -5, or maybe -49999. So that is just another way to write that is like that. That's another way to write it. If you work out what that says, you do get this.
So what's that will help us?
That's where we're going to.
What is this useful?
In what way?
Are we even gonna see this like in calc one?
You'll see this in further math classes, yeah. And more importantly, you'll see this now.
If we know like we'll end up the same thing, can we divide like 2 by 29 and we will get the first one?
Say again, sir?
Oh, no.
All right. So here, oop, yeah.
I'm still wondering how you got that cosine
It's not necessarily.
So here's the form. So all I have to do is figure out what R is and what theta is, and plug it back in. It's just like mx plus b. Wherever the hell you get m from, wherever the hell you get b from, you plug it back in. So I got R from here, I got theta from here, plug it back in.
No, thanks.
Okay. So let's start to look at why this is useful. Let's start to look at why this is useful. Okay. Guys, so is everybody cool with what I've written up there so far? You understand how that works? So I certainly could figure out 2 complex numbers. No problems up here. There's a number here that I could write in this form. There's a number here that I could write in this form. Doing everything we just did.
And we put a 2 underneath.
So the neat thing is, this is still not exactly to the point where I'm showing you why this is really cool, but we're getting close. Z1 times Z2, the shortcut I could do for this, and this is on page 558. Now, what this leads to, and again, I just said, this is not incredibly amazing yet. What this leads to is a shortcut for raising any complex number to any power. So here, these are 2 different complex numbers. So here's a shortcut in how to multiply them. And I'm not going to go through the steps. It's in the book. If you go ahead and multiply these out, FOIL this out, you could use the sum formulas for cosine and sine to recollect everything. That's the idea. You're going to get all these parts to this, but then you recollect them using the sum formulas. Not a big deal. What really is neat is if I have z to the nth power. So really what that is repeated application of this. If I multiply z by itself, by itself, by itself, n times, I can use this over and over and over and over again. Every time I multiply, I'm going to pick up another theta. Let me make sure everybody's with me. I'm using the same z in this case. So theta is going to be just theta, not theta 1 and theta 2. Theta is the same. It's the same z. So if I do z squared, that would be r squared. Are you with me so far? So here, z is this. So z squared would be r times r squared. Cosine theta plus theta, 2 theta, plus I sine theta plus theta, 2 theta. So z cubed would be r cubed cosine 3 theta plus I sine 3 theta. So what's z to the nth power? R to the nth. So for example, here's where I might get some of you guys to buy into it. Part of me, the entire part of me wants everybody to buy into it, but even if you don't, you still have to know how to do this.
Thank you.
Who amongst you Who amongst you? What the hell is that? Who amongst you? Who? Who amongst you? I like that. That's awesome. Who dare challenge? Who would want to sit down and do this out?
I know.
You follow? Who would want to sit down? What would actually have to happen for this to work? You have to multiply that by itself, and then again, and then again, and then again, and then again, 20 times, right? Well, that sucks major. Now, does everybody agree with me that in general, any complex number to some big power, I really don't feel like doing?
Yes.
That would be basically busy work. But sometimes I have to. Sometimes in a situation where that comes up, I actually have to. Believe it or not,
And
it happens.
situation?
And during possibly electricity, definitely.
Oh.
Right? Believe it or not, I think I've said this before, but you'd use complex numbers to designate parts of electromagnetic fields. That could show up. And there's other places where complex numbers could show up. So I might have to raise it to some power. Don't want to do it this way. No. So instead, I can do it this way. Now, I have to first rewrite that in the right form. Right? What's R going to be? So if I take this complex number and I want to put it in this form, what's R going to be? Yeah, square root of 1/2 squared plus 1/2 squared. Right, so square root of 1/4 plus 1/4, square root of 1/2. This is still 8/3, oh yeah. It's a lot of talking in 8/3. Right, which I can write as root 2 over 2, is that cool?
Oh, 45 degrees.
And some of you guys, you might start to realize, you might get to the point where you don't have to do this. If both the sides are the same length, this is going to describe a triangle, right, if I were to draw it. Both the sides are the same length. That must be an isosceles triangle, and in this case, the angle has to be, in this case, it will be 45. Let's see, how would you work that out just to make sure? Tangent theta would equal 1. So theta would be 45 degrees.
Sorry.
One word that time.
Just went blank for a minute. We're like, wait.
All right. So to rewrite this, this is this. Where we go? With me? So far, so good? I'm going to keep going anyway. Here we go. So now if I raise both sides to the 20th power, what's the shortcut way to rewrite that? Hold on. Can I take the top here off?
Yeah.
What page is that formula on? What?
559. How can I rewrite the inside now?
Wait, you yeah, go back.
Okay.
Oh,
So we got this here.
Another one, I got a raise. It's too late. No notes for you.
Page 559 has the
Oh.
formula on it. Now here we rewrote this complex number in this format. So now when I raise it to the 20th power, this side I would have to FOIL it out multiple times. This side has a shortcut to it. Yes, ma'am. Say again? How does root 2 over 2 become tangent theta 1? Tangent theta is defined to be b over a. What's b? What's b?
A letter.
Here's a plus bi. So b is 1/2, a is 1/2.
come you had to even do that to know that tangent was one?
I'm not sure how else I would know otherwise. In this specific case, there are geometrical ways you can figure out the angle is going to be 45 degrees. I'm trying to do it in a little more general terms, what you have to do no matter what these are. To figure out the angle, you set up tangent theta equals b over a. In this case, that equals 1.
So you just separate, so it is. I was trying to figure out how you went from r equals 2 over 2 to tangent equals 1, but those are just two separate questions.
Yeah, so here's what I'm trying to write. That form, I have to figure out what r is, check, and I have to figure out what theta is, check. And then I can just throw them back in. So it sounds a lot like those problems from algebra, believe it or not. Find the equation of a line that is perpendicular to this line and goes through this point.
Oh, they
Because you have to find a slope, check, and a point. They gave it to me, check. And then you can start throwing stuff in, right? Same damn thing I'm doing here. I got a general form for a complex number. I have to find the different parts of it, and then I can throw them in. If you want to verify it, you can actually do root 2 over 2 times this to show that it does come out to be 1/2. Okay, go.
Okay, now we multiply the whole thing by,
So the original question is, I want to raise this to the 20th power. I don't want to raise this to the 20th power directly, because it would involve a bunch of foiling. Way too much foiling for me to even worry about. But now I can raise it to the 20th power quicker. What would be in here?
45 to the 20th.
20 times 45. Yeah. Because the rule is...
On that root 2 over 2, that'd be 29 figure.
Yeah, 20. Yeah, thank you. Because the rule we wrote up here is that r cosine theta plus I sine theta to the nth is r to the nth cosine n theta plus I sine n theta. That's the rule. And that rule came from repeated applications of sine and cosine addition formulas. That's all that was.
So it will be 20 times 45?
Beautiful. Which is
A lot.
Does anybody have an idea? How do I actually evaluate this? This might be something I can do by hand.
360 minus 360.
Yeah, so subtract 720, a couple 360s, and what do I get? 180. So this is actually cosine 180 plus I sine 180. So what I get? Root 2 or 2 to the 20th. Cosine 180 is
1.
negative 1. Sine 180 is 0. So just get this, whatever the hell this is.
Do we have to raise it or like whatever?
Oh, it's fine like that.
Okay. I like it. Now let me just take notes, please.
Okay.
No,
This is
no.
page 559.
I don't care. I like to write it from there. It makes it easier. But I can't be writing it.
Turning those pages, I can get a paper.
If you have your book with you.
Oh,
my
that
book's at
too.
home.
That too. Should I give you any consideration for not having a book? I don't
No,
know.
it's really heavy.
Oh my God. Oh, first world problems. Now, the even more interesting thing, that's pretty cool in its own right. And if you don't think so, I don't care. That is actually really cool. I could raise that to the 5 millionth power in one step, right? Could never do that before, and now you can. That's pretty damn cool. But the more interesting one, I think I said earlier, I think it's more interesting. There should be how many answers to that equation? 8. But how many can I get directly? I could get not many directly, because this is not an easy problem to do. It's not a cubes, it's not really a... I could do squares where I bring in complex numbers, So I could simplify this. I could factor this to be x to the fourth plus square root of 64i, so 8i, x to the fourth minus 8i. Are you guys semi-cool with that? Remember, x to the 8th minus 64 would be x plus 8, x minus 8. This is a situation where complex numbers were created for. I need two numbers who multiply it by each, and it makes it, it doesn't change the sign. Plus times negative actually comes out to be plus. Because I squared is, what's I squared? Negative 1. Cool. So I can keep going in that way. And here I'm going to get to a point where it's a little freaky. I'm going to get radicals of I, which is really strange. So what I'm hoping is there's an easy way to do powers here. There should be an equally easy way to do roots, because roots are powers. So those of you following along, this is on page 560. Let me do this. One last thing, we'll take a break.
Hold on.
So if z is
Okay, I just want something that okay, so that whole thing you said it equals to negative square root of 2/2 raised to the 20th power. But what is equal to that? Is that z? Because you just have the equal sign, but it doesn't
so
match
this is the problem,
I know.
and that's the answer to the problem.
Oh, okay, so
Because that's what equals that. So that equals that.
okay. Sorry.
So here, if I want the nth root of z, if I want to find the nth root of some complex number, that's the same thing as raising z to the 1 over n. So it should be somehow related to this. So I would expect this to be something like this to start with, right? The nth root of r. Okay. And inside it happens exactly the way you would think. When I raise it to a power, I end up multiplying the arguments of cosine and sine, right? Here. So when I take the nth root, I should end up dividing those. And here we can be a little more precise. Oof. Okay. So when you first see this, it's like anything that you see in this class. It does not immediately make sense. You're like, what the hell am I going to do with this? So we got this here?
Yep.
Okay. Now, taking this,
Does it have a name, the property that you just raised, the one from 5
the what now? Sorry?
like a name, like the property of law?
Not really, it's just nth powers. It's actually De Moivre's theorem, but I just call it the nth powers theorem.
The n.
And this is the nth roots theorem. So in this problem, I really want to do this. But if you plug that in your calculator, for example, it's going to freak out because that would be complex. Right? So I must have 8 complex answers here. That's going to give it to me directly. The one thing I have to do is the same as before, and it kind of freaks people out a little bit. Does that look like a complex number?
No.
And the right answer is yes, because a plus bi, if I make b 0, that's all the real numbers, right? If I make b 0, I just end up with 8. So 7 is 7 plus 0i. So complex numbers are just one level above real. They contain all the real numbers plus the ones where b is not 0. Okay. So all complex numbers do.
What's W?
Don't worry about W.
It's all over the
I don't like this book uses W, it's not necessary. Alright, don't worry. We'll do it this way, sorry.
Come down. Slow.
So how do I write negative 64 in this form here? It actually is kind of nice. If b is 0, for example, if b is 0, tangent theta, I'm trying to write negative 64 in that form. What's, in this case, a is negative 64. What's b?
Undefined.
0. 0. So what's tangent theta going to have to be?
0.
0. 0 over negative 64 in this case is 0. So what's the angle going to be?
0.
0. I love it. So theta is 0 degrees. That's at least the reference angle there, in a way. All right.
So everything goes up.
Now, which quadrant am I in? And not really in a quadrant, but the one thing I have to be careful about, where would negative 64 be? Back here, you with me?
180.
Yes. So I really want to make this not 0 degrees, but 180 degrees. Okay, so 0 is like the reference angle. A 0 reference angle is weird, but all I was trying to say is it could be pi or 2 pi. So in this case, it's pi. So I end up with a negative real piece. So I'm back here. Maybe. So theta is 180. What's r going to be? Square root of negative 64 squared plus 0 squared. So 64. Yes?
I see like a lot of R's and Thetas. Are we gonna keep using that in the polar thing?
Yeah, this is very related to polar coordinates. Because when I graph complex numbers, I can think of them as having an angle to turn to them and a distance to go out to them. So this really is directly related to polar coordinates. It isn't polar coordinates, but it's directly related. Okay, so what would negative 64 be in this form? It would be 64 cosine 180
Sine 180.
plus I sine 180. Just to check, cosine of 180 is
0.
negative 1.
Yeah, that's
Sine of 180 is
0.
0. So I lose that complex piece, and I do get negative 64, so it checks. So what I want to do now is take the 8th root of this. To solve that equation, I want to take the 8th root. So using the rule that we've got, that would be the 8th root of 64. Just using the rule that I have over there. Kind of a long ass rule, so let me see if I can fit it all up here. Cosine of theta, so what's 180? And let's put it in terms of pi here, since I have pi in there. Over 8. How are we doing so far? I'm just plugging and chugging now. So here I put the 64 to the 1/8 cosine of pi plus 2k pi over 8. Because n is definitely 8. I want the 8th root. Plus, now this is where I'm going to need your permission.
Go.
All right.
Whatever. I'm like trying to copy a few times.
Plus I sine. That's why it kicks ass. You have a teacher that records this lecture. Plus 2k pi over 8.
Yeah, if you could see your writing.
Just plugging and chugging, right? Okay. And the last piece of this, the reason that k is important, and why they put the wk there, but you don't really need it. Here's the k. This works for k from 0 and up to n minus 1. So in this case, if n is 8, I'll have 0, k equals 0 gives me an answer, k equals 1 gives me an answer, up to 7, that will be 8 total answers. Kind of with me? So just look at one answer real quick. If k is 0, what's the 8th root of 64? 2. Is it? Yeah, it's root 2. Thank you. The 6th root of 64 is 2. The 8th root of 64 would be the 4th root of 8. Root of, yeah, the 8th root of 2 to the 6th power. That's the 4th root of 2 cubed. 2 to the 3/4. So that's whatever number you get out of your calculator. If k is 0, I get cosine of pi over 8. And then that you can put in your calculator to figure out what the actual number is. Let me see if they did that for me. Not really. Oh, I did, of course, a different one than them. Great job. But if you actually do this in your calculator, you'll figure out what this complex number is. And you can do that for each case. K equals 0, K equals 1, and K equals 2. So obviously, I'm not going to go insane and give you like a 20th root or something, because that would take a long ass time to write out all the answers.
Also, not the tower for each K.
That's the...
Like for for like test purpose, we have to solve.
Yes.
K like K0.
Plug a 0 in, plug a 1 in, plug a 2 in.
Okay, cool.
So let's go ahead and I'll tell you this. Let me tell you something.
I'll keep you.
I have a 3 o'clock presentation that I'm doing for some adult reentry students. So we are definitely getting out a little before 3, because then I have to run off in that direction. If I can get a compromise, if I can finish out chapter 8, just do section 8.4, then I'll let you guys out whenever that's done. If we take a break,
That will complicate it.
that will, yeah.
But after we take a break, so we're not gonna do another. Would you really distribute?
Let's starting. So let's hurry up.
Oh my God. It's just a constant
First of
parade.
all, you can put that imaginary number in the calculator.
Yeah, you actually have an imaginary mode.
If it's imaginary mode.
Okay, I'll
So how
just do that.
and do the A through negative.
Where is it?
So, why do we spend time graphing by hand? It's not just because Jeff is some megalomaniac who likes to watch students squirm. It's because you actually get something out of it, right?
A plus B on.
So you have to do the A plus B
Answer.
under your calculator mode.
Look at you go. All right.
Plug it in.
Be like A plus BI.
Let's get out of here. Come on. Hurry,
So
hurry.
we can't do another one if you go?
No.
Yeah, let's do it. Yeah.
I'll let you guys try it out, and then we can do some homework questions next time.
Tomorrow we can.
So are we gonna work
Not
on
tomorrow.
Monday?
Okay.
Are we having test on Monday?
Quiz? No, the quiz we're going to push back until Wednesday.
We're gonna have another quiz?
The quiz that was supposed to be Monday will now be on Wednesday.
Oh, I didn't even know that. Sorry.
Yeah. Yeah, this is section 8.4. Oh, yeah. So the quiz on Wednesday will be chapter 8. Yeah. Say again? Sorry?
See, I'm not the only one lost.
Yeah, because you took away one of the tests.
Oh, yeah. Let's have another one. It's not a big deal.
Okay. Wait, so we just have.
Some of you realize why I cry a little bit? I think some of you guys realize that. Not some of you. Everybody got one of these? It actually has in blue the quizzes that I'm talking about right now.
I know, but I didn't realize that you took out the test.
Oh yeah.
Everybody has this also that says test 4, that's the last test.
Oh, my best friend's birthday.
What's that?
Yes, we do.
Yeah, we do.
Wait, what?
Thanksgiving is on Thursday. Yeah, really got Thursday, but
I gotta go to Friday class.
It's just too bad you don't go to Mesa where they get the whole week off. But you don't, so we're here
My
Wednesday.
kids in National City District.
You're gonna give us a test, like before Thanksgiving. Day before Thanksgiving.
A quiz, yeah. A test, I wouldn't do that to you. All right.
I was gonna ask if I could bring my niece to class so she would stop complaining about her research.
Parametric curves, equations. All right, so far in math, we've had several different ways of plotting points, for example, and we've actually looked at like cardioids, which looks like, do it the other way, looks like however you want to say. So we've seen different ways of plotting equations, but every way we've looked at, one variable has been directly dependent on the other one in some way. You with me so far? So like we had r equals 3 sine 2 theta, and we graphed that. So r is directly dependent on theta. we're now getting to a point where we're going to try to do it so that each variable itself is dependent on some third variable, which is actually more related to real life. Very often we have what seems to be a correlation between two things, but there's some third thing that's influencing both. So it's like we're looking at the behind the scenes. You can get some really nifty graphs from this. And there is a mode on the calculator that we'll be looking at that we can graph these things on the calculator, which is nice. So let me give you an example. Before, we would have an equation like this. You can make an XY table a long time ago and plot it, and you'll end up with a nice little parabola, a little bit skinnier than normal. Okay, no big deal. So you'll plug in an X, you'll get a Y out. You plug in an X, you get a Y out, and so forth. Now, we're going to have something like this. Let's make this more interesting. I was trying to make it more interesting, but it's bad. So when you make, I am going to ask you, and I will put on the quiz, I'll actually put the table on there. I want to see you creating some of these tables. And here's how I would create a table for this. I would actually need X, Y, and T. So sometimes I'm going to give you, and the book is going to give you an interval for T. T can only be from 0 to 3 or something like that. Like sometimes you have to give somebody that, or else it's just going to go crazy forever. So for example, if I put 0 in there, X would be 0, Y would be 0. Not a big deal. So the point I would actually plot would be this point here. That is the hidden behind the scenes controller of both X and Y. Are you guys kind of with me? This is a very, not a huge shift in the way we've looked at this before, but it's kind of a subtle shift that actually takes a little bit of getting used to. If I make T 1, X will be 1, Y will be 2. Okay, and so forth. So if I make T negative 1, 1, 2, because when I square it, of course, it stays positive. And if I make it 2 or negative 2, just give a couple more points.
4.
X would be 4. Y would be 8.
4.
Okay. So to plot this, I would just plot those points. 0, 0, 1, 2, negative 1, 2. And I mean, better scale. Let's see. 1, 2, 3, 4. Okay. So here's 1, 2, negative 1, 2, and then 4, 8, and negative 4, 8.
But why are you going on the negative side if X and Y are positive?
Oh, I'm being really stupid. Thank you. So 0, 0, 1, 2, 4, 8, and 4, 8, so they match up there. Thank you. And so I just get this side of this parabola. I think it's trying to be, no, it's not a parabola. It'll be a straight line. And if X is T squared and Y is twice T squared, Y will always be double X. Now, when I see this, can I see that immediately? No, I see these squares in there that might make me think it's going to end up a certain way. But I can see from the work I'm doing, it is always twice X. And I could actually take these, and this is a very simple one to start with, but I could take these and eliminate the T squared. And this was a simple example. Y equals twice T squared, which is X. So Y equals 2X. Say again?
How do you get negative 1 on T?
Because T can be whatever I want it to be. T is my input variable now, so I can make T whatever I want to be unless they give me some restricted domain for it. So here I didn't tell you what T could be, so T could be anything. T is just like X used to be. Here, what can you put here? Anything you want. So here I can put anything I want to. So they get a little more interesting when you do stuff like